Welcome to Vectors and Equilibrium. In this video, we'll explore the fundamental concepts of vectors, their operations, and how they relate to equilibrium in physical systems. Let's start by understanding what vectors are. Unlike scalars, which only have magnitude, vectors have both magnitude and direction. Examples of vector quantities include velocity, acceleration, force, and displacement. In contrast, scalar quantities like temperature, mass, and time have only magnitude. How do we represent vectors? Vectors are commonly denoted with bold letters or with an arrow on top. In this video, we'll use an arrow above the letter. A vector can be represented by its components along coordinate axes. For a two-dimensional vector, we have x and y components. The magnitude of a vector, also called its length or norm, is calculated using the Pythagorean theorem. Now, let's explore vector addition. To add vectors, we add their corresponding components. Graphically, we can use the tip-to-tail method. Place the tail of the second vector at the tip of the first. The resultant vector goes from the tail of the first to the tip of the second. Another approach is the parallelogram method. Place the vectors tail to tail and complete the parallelogram. The resultant is the diagonal from the common tail to the opposite corner. Vector subtraction follows similar principles. To subtract vector b from vector a, we add the negative of b to a. Graphically, we can reverse the direction of the vector being subtracted and then use the same addition methods we just learned. In terms of components, we simply subtract the corresponding components. When we multiply a vector by a scalar, the result is a vector with the same direction but scaled magnitude. If the scalar is negative, the direction is reversed. In terms of components, we multiply each component by the scalar. The dot product, also known as the scalar product, is an operation that takes two vectors and returns a scalar. For vectors a and b, the dot product is defined as the product of their magnitudes times the cosine of the angle between them. In terms of components, it's the sum of the products of corresponding components. The dot product has several important properties. It equals 0 when vectors are perpendicular, it's positive when the angle is less than 90 degrees, and negative when the angle exceeds 90 degrees. The cross product, or vector product, takes two vectors and produces a third vector that is perpendicular to both input vectors. For vectors a and b, the magnitude of the cross product equals the product of their magnitudes times the sine of the angle between them. The direction follows the right-hand rule. If you curl your fingers from vector a to vector b, your thumb points in the direction of the cross product. In terms of components, we can calculate it using this formula. Now, let's discuss equilibrium, a critical concept in physics and engineering. A system is in equilibrium when there's no net force or torque acting on it. For translational equilibrium, the sum of all forces must equal 0. For rotational equilibrium, the sum of all torques or moments must equal 0. Let's look at a simple example of equilibrium. Imagine a block resting on a table. It's in equilibrium because the weight force pulling down is balanced by the normal force pushing up. Let's look at a more complex example of equilibrium. Consider a simple bridge with a weight in the middle. For the bridge to be in equilibrium, the supports must provide balancing forces to counteract the weight. If we analyze the forces, we need the sum of all forces to equal 0 and the sum of all torques around any point to also equal 0. From these conditions, we can calculate the reaction forces at each support. To wrap up, we've covered the fundamental concepts of vectors and equilibrium. We learned about vector representation, addition, subtraction, and scalar multiplication. We explored dot and cross products, which give us powerful tools for analyzing vector relationships. Finally, we applied these vector concepts to understand equilibrium, a state where the sum of all forces and torques equals 0. These principles have wide-ranging applications in physics, engineering, computer graphics, and many other fields. Thanks for watching. I hope this video helped you understand the concepts of vectors and equilibrium.